A start of a new unit, and we will trimly iron a regretting goth. Or maybe that's not what we're going to do. Oh my goodness. The new unit has the same general topic as the previous unit, right triangle trigonometry. And in fact, we're going to advance into triangles that are not right triangles. But we're going to start today with right triangles. Issue seemed to be from the previous unit that some of us are having a little bit of difficulty showing work, so I want to kind of stress a couple things that right, just having the answer is not nearly so important as can you communicate why you have that answer. So let's think about back in elementary school, teachers trying to show a student how to do long division. Student says, hey, come on, I don't need to show step-by-step work. The calculator's going to do it for me. Okay, so we're going to jump in a time machine, do a little bit of time travel. This is a lengthy PowerPoint. I apologize in advance. But we got to get in the time machine, and we got to go to the past for just a moment, and then we'll go to the future. All right, so let's go back to elementary school, and let's get the whole family to show up. All right? A long time ago. Oh, wait, no, it's not Star Wars. In a classroom far, far away. Okay, so let's get that whole family to show up here. I want to find 4,714 divided by 5 using long division. Here comes that whole family. Right, we're going to have Dad, Mom, sister, brother, and Rover. Dad, of course, reminds me to divide. Mom reminds me to multiply. Sister, subtract. Brother, bring down, bring it down, bring it down, bring it down. And then Rover, repeat. Like Rover, do it all over. And then Rover has a special surprise at the end for remainder. Okay, so how do I do long division? Well, Dad says divide. How many times does 5 divide into 47? 9. Okay, Mom, multiply. 9 times 5 is 45. Sister, subtract. 47 subtract 45 is 2. Brother, bring down. So I bring down the next number. Rover, repeat. Okay, so 5 divides into 21 4 times. 5 times 4 is 20. Subtract, I get 1. Bring down, 14. Rover, do it all over. 5 will divide in there twice. 5 times 2 is 10. 14 subtract 10 is 4. Bring down, oh, there's nothing else to bring down. And so Rover magically becomes remainder. He says, hey, the remainder is 4/5. Right? Remainder of 4, we're dividing by 5. Now, why is it so important to know how to do that by hand when we have a calculator that will do that for us? Okay, let's go to the future real fast. We're going to go visit Algebra 2 super briefly. I do not expect you to understand this, but I want you to see this. The whole family gets involved if I'm doing long division. All right? I have to divide, I have to multiply, I have to subtract, I have to bring down. Divide, multiply, subtract, bring down. All right? Divide, multiply, subtract, bring down. Uh-oh, there's nothing to bring down. So I've got my remainder, right? It's the same algorithm. But if I don't understand how to do it with plain old numbers, I'm not going to understand how to do it with polynomials, right? I have to understand the methods that I have learned, right? Everything that's been in those lower math classes is going to be utilized in advanced math classes, right? Show thy most excellent work. We've got to show work. So let's revisit some concepts we've already worked with. Some of these concepts we've been exposed to in geometry, but some should predate geometry. Right? You should be able to simplify square roots. This should be like old news. Square root of 50. Okay, I'm thinking 25 times 2. Square root of 25 is just 5. There's an answer. Square root of 63. I'm thinking 9 times 7. Square root of 9 is 3. There's my answer, 3 root 7. Square root of 16. Don't overthink stuff. Square root of 16 is just 4. Right? Sometimes it works out nice. Square root of 21. The only thing I can think of is 3 times 7. But I cannot take the square root of 3. I cannot take the square root of 7. So I should actually just leave it as square root of 21. That would be my answer. Right? Sometimes they will not simplify. Now, what if you're not the world's best at picking the correct pair of numbers to start with? Well, if I encounter 72, I could try 9 times 8. And of course, I come up with 6 root 2. I could try 4 times 18. I can go step by step. Surprise, surprise. Again, I got 6 root 2, but it sure took me a long time to get to the correct answer. Shortest, most direct route is 36 times 2, because the square root of 36 is just 6. So, how do I know to pick 36 times 2 so I can take the most direct route and not get sidetracked? I could list every single pair of factors. Right? I could do 1 times 72, 2 times 36, 3 times 24, 4 times 18, 6 times 12, 8 times 9. I can then identify the perfect squares and then say, okay, of all those perfect squares, which one is the largest? Well, hey, it's going to be 36. Since 36 is the largest perfect square on that list, I should do 36 times 2. Now, if you're not so hot at listing factors, you may want to try a factor tree instead. Pair of numbers for 72, maybe I'll choose 6 times 12. 6 becomes 2 times 3. 12 becomes, well, I could either do 4 times 3 or I could do 2 times 6. Here I did 2 times 6. Finally, I see a 6. I can make that 2 times 3. I can grab a pair of 2s. I can grab a pair of 3s. Multiply all that together and I get 36. Notice there was a leftover 2 that was not used. 36 times 2 would be the magic pair to use. Now, I think simplifying square roots like that has not been the biggest issue. Instead, the larger issue has been, what do we do when there's a square root in the denominator? Right? We do not want to have square roots in the denominator. I'm always allowed to multiply by the number 1 without changing the value. Right? If I multiply by the number 1, I get the same old thing back. But I'm going to disguise the number 1 as the square root of 2 over the square root of 2. Why did I pick root 2 over root 2? Because I'm trying to work with that square root of 2 that was in the original part of the question. Of course, root 2 times root 2 becomes root 4. And square root of 4 is plain old 2. I could have also thought of that as root 2 times root 2 is root 2 squared, and the squared and the square root undo each other. Notice the root 2 that originally was on the bottom of the fraction is now on top. And notice that what used to be a root 2 on the bottom is now a plain old 2. Of course, 6 is really 2 times 3. The 2 on top and the 2 on the bottom cancel out. There's my final answer. Let's try another example. Let's multiply by the number 1. Of course, this time I'll disguise the number 1 as root 7 over root 7. Of course, 7 times 7 is 49. Square root of 49 is 7. Again, notice the square root of 7 that was on the bottom has now magically appeared on top. And what used to be a square root of 7 on the bottom is now a plain old 7 on the bottom. Right? That 5 has just been sitting there. This time, 5 over 7 will not reduce. So that's the final answer. Can't do anything. We're done. Another example. Okay, got to get the square root off the bottom. Let's multiply by the number 1. This time, how do we disguise the number 1? Root 6 over root 6. 6 times 6 is 36. Take the square root. Once again, notice that square root of 6 that started on the bottom of the fraction has mysteriously made its way to the top of the fraction. And that square root of 6 on the bottom has now become a plain old 6 on the bottom. And of course, this fraction will reduce. 6 is 2 times 3. Cancel out the 3's. There's my final answer. Notice I do not try to do anything with that square root of 6, right? I cannot reduce. I know 6 is 2 times 3, but that 2 is stuck inside the square root symbol. It will not cancel with the 2 on the bottom, right? We're stuck. Final answer. Fast forward to what we were doing last chapter. Let's see if these square roots come into play. Oh my goodness, sometimes they do. If I'm asked for an exact value, I do not want some weird decimals coming out of that square root symbol. I will always start by writing a squared plus b squared equals c squared. Get that down on paper first. Plug in the numbers in the appropriate locations. Square root of 29 squared becomes plain old 29. Why do I insist on writing down this equation? Some students get in a hurry. They want to grab a calculator. They want to square both numbers, and they want to add them. Notice I am not going to add 29 plus 9 here. I have to subtract 9 to isolate the variable. Right? I had to subtract 9. Of course, square root of 20 can be simplified. 4 times 5 is what comes to mind to me. Right? If I had tried 2 times 10, I would have said, whoa, I can't do anything. I better try something different. Or you could have made a factor tree and you would have said, hey, look, I got a pair of 2's, and hey, I got a leftover 5. But there's our answer. 2 root 5 is the exact value. Right? Always want to simplify. Now, sometimes there's really no work to show. Right? If I'm looking at this triangle and I want side K, I'm thinking, well, duh, half of 10 is 5. Right? Do I really need to show work on that? Oh, side M? Well, let's just multiply that by root 3. 5 root 3. Duh. But then other times you really need to show work, right? Because look what's happening here. Now I'm starting with the side opposite 60 degrees. So if I want the side opposite 30 degrees, I'm going to have to divide by square root of 3, right? Not multiply, but divide. Okay, so I'm going to multiply by the number 1. Look at how I disguise the number 1. You can probably predict that we're going to end up with a plain old 3 on the bottom. Right? The square root of 3 that was originally on the bottom has magically gone on top. The square root of 3 that was on the bottom has magically become a plain old 3. Now, to reduce, that square root of 3 inside the square root symbol cannot cancel with anybody. Right? It's inside a square root symbol. But that 21 I can rewrite that as 3 times 7. And the 3 from the 3 times 7, that can cancel. There's my final answer, 7 root 3. Now, I know the hypotenuse will just be twice as big, so I could be lazy and just say, hey, double it, you get 14 root 3. I could say, you know what, though, if I showed work for that, I should probably show work for the other one. So I can say, hey, I know t equals 2 times w. And so I got to do 2 times 7 root 3, and I get 14 root 3. Right? Usually if I have to show step-by-step work to get one of the sides, I'll show step-by-step work for the other side. Right? You kind of got to judge it, right? Because sometimes the question's like, hey, I can do it in my head, piece of cake. Other times you're like, whoa, I really need to show step-by-step work to justify where my answers are coming from. Of course, sometimes instead of A, B, and C, we use different letters. So I'm like, aha, it looks like I'm focusing on angle E. All right. Again, I'm going to write down E squared plus G squared equals F squared. Right? F was the hypotenuse, so that's why F squared has to be the part that's off by itself. I can plug in 18 as being across from E. 24 has to be G because it's across from G. If I need to use a calculator for that step, I can. And if I need to use a calculator for that step, I can. And if I need to use a calculator here, I can do that because it came out to be a nice plain old 30. Now, because I'm focusing on angle E, that's going to affect some of the names of the sides. The hypotenuse obviously is not going to change. The hypotenuse will always be across from the 90-degree angle. And so that's going to be the hypotenuse is 30. But because we're studying angle E, the legs can now be determined which one is opposite and which one is adjacent. 18 is opposite. 24 is adjacent. So if I want the sine of angle E, again, this is where I want to remember SOHCAHTOA. SOHCAHTOA reminds me that sine is opposite over hypotenuse. 18 over 30, reduce the fraction. SOHCAHTOA also reminds me that cosine is adjacent over hypotenuse. So I put adjacent over hypotenuse. I can reduce the fraction. There's my answer. So those are my answers for sine and cosine. Right? Direction said write the answer as a fraction. So leave them as a fraction. Notice I never had to touch the cosine button or the sine button on my calculator. My favorite type of question, because there's no picture. I love this type of question. It's like, hey, can you find the sine of A? And you're like, oh, no. Okay, well, if there's no picture, what do? We draw a picture. Let's label the corners A, B, and C. C will be the 90-degree angle. Since I'm focused on A, well, the hypotenuse is a piece of cake, right? That's going to be the long side across from the 90-degree angle. But if I'm focusing on A, however I drew my triangle, side BC has to be opposite, right? Side BC is opposite angle A. And then side AC is adjacent to angle A. SOHCAHTOA, cosine is adjacent over hypotenuse. I now know that 15 is adjacent, 17 is hypotenuse. That's where they have to go on the picture. I'll always start by writing down the A squared plus B squared equals C squared, because sometimes I end up adding, sometimes I end up subtracting. I cannot just do this on autopilot. I have to know which one is correct. So little b will be 15, little c will be 17. Use a calculator for that step if need be. Aha! To get a squared isolated, I actually have to subtract. Right? Students love to go into autopilot. They like to do 15 times 15, 17 times 17, and then you just automatically want to add those numbers. You can't just automatically add. You've got to have the work shown so you know whether or not you should be adding or if you should be subtracting. 64 seems way too big. Oh, I forgot the last step. Take the square root, I get 8. Again, SOHCAHTOA reminds me that sine is opposite over hypotenuse. Opposite 8, hypotenuse 17. There's the answer. I know this video was kind of lengthy today, but I really need to reinforce that we have to show work and also give you a chance to practice a little bit more with those crazy square roots and simplifying square roots. Notice there's no mention of any IXL assignment. Right? Look what just blended into the woodwork. Let's carve it out. We've got a worksheet. Let's get a better look at some wood here. There we go. That's a better look at some wood. Nice little forest. All right, just a worksheet. There is no IXL.